In this lesson, we want to apply the confidence interval structure, the point estimate plus and minus a margin of error, to describe the mean of a population, particularly when the population standard deviation is known. Say that we're interested in understanding the ability of a particular kind of lumber to withstand loading. Eastern white pine is a widely used timber for construction lumber in the northeastern United States. We collect a random and representative sample of 40 similarly sized pieces of eastern white pine lumber and measure the modulus of elasticity in megapascals obtained 1 minute after a loading is applied. We obtain the following results for each of the 40 pieces of lumber. A reminder of the notation. Our random variable y is the modulus of elasticity, and y sub I represents the ith realization of that random variable. Here, I ranges from 1 to n equals 40. Our point estimate for the mean modulus of elasticity would be the sample mean of our n equals 40 observations, 13,985 megapascals. But we understand that point estimates don't tell the full story. They boil the entire distribution of sample data, as seen in the histogram, down to a single value. We would prefer to estimate the population mean modulus of elasticity for eastern white pine lumber with a confidence interval. There are two situations in which we may find ourselves when looking to calculate a confidence interval for mu. The first is where the standard deviation of the population, sigma, is known. The other is where sigma is not known and must be estimated from sample data. Let's first address the situation where sigma is known. Within this situation, there are three cases. We use the standard normal distribution, z, to represent confidence in the calculation of our interval for the first two cases. In case 1, the population is known to be normally distributed, and the sample size can be small, less than 30 observations. In case 2, so long as the sample size is sufficiently large, 30 or more observations, there's no restriction on the population distribution. In the first two cases, we assume that the sample is normally distributed, either because the population is, in case 1, or because the central limit theorem suggests that we can with a large enough sample in case 2. We will address case 3, where we know the population distribution is something other than normal, and our sample size could be small, later in the course. For cases 1 and 2, the magic number for sample size is 30. As we saw in the discussion of sampling distributions, n equals 30 is mostly arbitrary. Generally speaking, the larger the sample size, the closer the distribution of sample means gets to a normal distribution, and most textbooks suggest the sample size should be 30. We'll address the magic n equals 30 assumption again soon. A note on the normality assumption. There are statistical tests that we can apply to a set of data to determine if data are normally distributed. We'll broadly discuss such goodness of fit tests later in the course. Popular goodness of fit tests, particularly for testing the normality of data, are the Anderson-Darling and Shapiro-Wilk tests. An easy, though less rigorous approach is to eyeball a histogram or the data you've collected to see if the data appear roughly normally distributed. Again, we want a 1 minus alpha times 100% confidence interval of the form of point estimate plus and minus a margin of error to estimate a population mean mu in the situation where the population standard deviation, sigma, is known. For cases 1 and 2, our equation for the confidence interval is y bar plus and minus z alpha over 2 times sigma over root n. We have our point estimate, the sample mean y bar, and we add to it and subtract from it a margin of error that's a function of variability, sample size, and confidence. Here, variability and sample size are included with sigma over root n, and confidence is represented with z sub alpha over 2. As sigma over root n is the standard deviation of the sampling distribution of y bar, we're essentially creating a set of bounds that are z alpha over 2 standard deviations away from the point estimate. We get the values of plus and minus z alpha over 2 from a standard normal distribution table. Back to our lumber example. Assume you know the population of eastern white pine lumber has a modulus of elasticity standard deviation of sigma equals 1550 megapascals. What would be a 95% confidence interval within which we estimate the true modulus of elasticity for the population of eastern white pine lumber will fall? We found in our sample of n equals 40 observations that the sample mean modulus of elasticity was y bar equals 13,985. At 95% confidence, the significance level would be alpha equals 0.05. When we look up z of alpha over 2, or z of 0.025, in the standard normal distribution lookup table, we find that plus and minus z of 0.025 is equal to plus and minus 1.96. Therefore, the 95% confidence interval is 13,985 plus and minus 1.96 times 1550 over the square root of 40, or 13,504.65 and 14,465.35 megapascals. That is, based on our sample of 40 pieces of lumber, we are 95% confident that the true modulus of elasticity for eastern white pine lumber falls between 13,504.65 and 14,465.35 megapascals. To have 95% confidence, or alpha of 0.05 significance, the value of z we use is 1.96. While we'll continue to use 1.96 in our calculations, 1.96 essentially rounds to 2. This suggests that when our confidence is at 95%, we capture 2 standard deviations on either side of our point estimate. Oftentimes, the z value is interpreted as the number of standard deviations away one value lies from another. And this is another reason why the word standard is used in the standard normal distribution. We'll discuss this more in the context of hypothesis testing in a later unit.